Hey everyone, if you're a Java developer, you know that multithreading is one of its most powerful features, but it's also one of its most dangerous. So today we're going to do a real interview-level deep dive into a topic that is absolutely critical in modern Java, thread safety and what is arguably its most elegant solution, immutability.
So, let's start with the absolute core of the problem we're trying to solve here. Imagine two people are trying to update a number on a whiteboard. One person reads the number 5 and wants to add 1. At the exact same time, another person also reads 5 and wants to add 1. Now, if they're not careful, they might both just erase the 5 and write 6, when the correct answer should obviously be 7. That chaos right there, that's called a race condition, and it is the absolute bane of concurrent programming.
And here's what that race condition looks like in actual code. On the left, you've got a super simple counter. Now, that little count plus plus operation, it looks like one single step, right? But it's not. It's actually 3. First, read the value, then add 1 to it, and finally, write the new value back. The problem is, multiple threads can interrupt each other right in the middle of those steps, and you end up with the wrong count. The thread-safe version on the right uses something called an atomic integer, which guarantees that the entire read-add-write operation happens as a single, indivisible step. No interruptions allowed. Problem solved.
Okay, so how do we actually fix these kinds of issues? Well, it helps to think of it like having a toolkit for thread safety. And a really great developer knows exactly which tool to pull out for which job.
And here's a quick look at the main tools in that kit. You've got the classics, like synchronization and locks, which are kind of like putting a bouncer in front of your data to let one thread in at a time. We've got the atomic variables, which we just saw in action, and then you have some more advanced strategies like thread local storage, concurrent collections, and the one we're really going to zero in on today, immutability.
Let's just touch on the most traditional tool for a second, the synchronized keyword. It is powerful, for sure. It creates what's called mutual exclusion, which is just a fancy way of saying only one thread gets access at a time. But, and this is a big but, that power comes at a really steep price. It can be a major performance killer, and if you're not super careful, you can create deadlocks where your threads end up waiting for each other forever, grinding your whole application to a halt.
But what if you could just avoid the whole fight entirely? That's the beautiful idea behind a stateless class. You see, if an object has no data that ever changes, no state, then there's literally nothing for the threads to fight over. A simple calculator service is a great example. Its add method only cares about the numbers you give it right now. It doesn't remember anything from the past.
And this brings us to a really crucial interview one-liner. Seriously, remember this one. If you're ever asked how to achieve thread safety, this is one of the strongest, simplest answers you can give. Stateless objects are thread safe by their very design. You've eliminated a whole category of bugs before you've even written a line of code to manage them.
So that idea of designing the problem away leads us to the most powerful concept in our whole toolkit, immutability. Instead of worrying about managing how things change, what if we just stop them from changing at all?
And let's be really clear about this. When it comes to thread safety, immutability is widely considered the best approach. It's not just another tool in the box. It's a fundamentally better, safer way to design concurrent systems. So it's really important to understand why it's so powerful.
The definition itself sounds almost too simple. An immutable object is an object whose internal state cannot be changed after it's been created, period. If you want to modify it, what you're actually doing is creating a brand new object with the new value, leaving the original one completely untouched.
So how do you actually build one of these in Java? Well, here's the recipe. First, you make all your fields final, so they can only be assigned a value one time. You make the class itself final, so nobody can come along and subclass it to change its behavior. You provide no setter methods, no way to change the data. And here's a critical one. If you absolutely have to include an object that can change, you make defensive copies. That means you create a brand new, private copy of that object just for your class, so no one on the outside can ever get a hold of it and change it.
And here it is. This is the payoff. Just like those stateless objects we talked about, immutable objects are inherently thread safe. You can share them, pass them between 100 different threads, and you never ever have to worry about synchronization or locks because you have an ironclad guarantee that the data inside will never be corrupted. It simply can't be. Now look, this isn't just some abstract academic idea. It is built into the very heart of the Java language itself. And for that, we can look at the perfect case study, the string class. I mean, have you ever stopped to wonder why one of the most common fundamental building blocks in all of Java was designed this way?
This right here is probably one of the most common and most revealing Java interview questions you can get. The answer isn't just one thing, it's this beautiful combination of thread safety, performance, and security. Nailing this answer shows you really understand core Java design. All right, so first and foremost, thread safety. In any real-world application, strings are everywhere. They're used for user data, messages, configurations, and they're being passed between threads constantly. By making them immutable, the designers of Java ensured this could happen without any risk of corruption, which has made life simpler for millions of developers.
Next up is a brilliant optimization called the string cool. To save a ton of memory, the JVM only keeps a single copy of each string literal. So if you have the word hello 1,000 times in your code, there's actually only one hello object in memory, with 1,000 pointers to it. This amazing trick only works because strings are immutable. Just imagine if they could be changed. Someone altering one reference would accidentally change the string for everyone else pointing to it. It would be total chaos.
This is a huge one, security. Just think about where we use strings. We use them for database connection URLs, for file paths, for security credentials. Now, if some malicious code could get a reference to your database password string and change it after you've already checked it, you'd have a massive security hole. Immutability gives you a guarantee. The value you check is the value you use. It cannot be tampered with.
And finally, performance. Because a string's value is guaranteed never to change. Its hash code, which is basically a unique number generated from its letters, can be calculated just one time and then saved. It's cached forever. This makes strings incredibly fast and reliable to use as keys in data structures like a hash map, which are used everywhere.
Okay, let's pull all of this together. Knowing the theory is one thing, but knowing how to talk about it and what mistakes to avoid is what's really going to make you stand out in an interview.
So here are the common traps. First, don't ever say that thread safety just means slopping the synchronized keyword on everything. That's slow and dangerous. Second, don't think atomic variables are some magic bullet. They're great, but they only solve problems for simple single values. Third, don't assume that creating new immutable objects is always bad for memory. As we saw with the string pool, it can actually save memory. And finally, don't just say string is immutable for one reason, like security. It's the powerful combination of all four reasons that makes the design so brilliant.
So, if you really want to leave your interviewer with a powerful, concise thought, here's the first half of a great closing statement. Draw this sharp distinction. Most thread safety techniques are about managing the problem of multiple threads changing things. Immutability is about eliminating the problem at the design level.
And this is the final, forward-looking point that ties it all together. This isn't just a clever trick from the past. It's the direction modern software engineering is headed. Building systems that are scalable, reliable, and easy to think about means favoring these simpler, safer patterns like immutability over complex, error-prone locking.
And we'll leave you with this question to think about. We've just spent all this time talking about how powerful and elegant immutability is, but in a world of complex performance trade-offs and constantly changing state, is it really the right tool for every single job? The real answer, as it always is in engineering, is it depends. Thanks for tuning in.